First, I would like to thank the organizers for organizing this session. This is a joint work with Ananta Acharya and Ratnasingham Sivaji. I want to give a motivation before I introduce the model that I'm interested in today. In 2018, we studied this particular elliptic boundary value problem where the parameter lambda influences the equation as well as the boundary condition. Here, this mu is an increasing function. And here are the three cases that we focused on for this model. F of 0 is 0, f of 0 is positive, and f of 0 is negative. In each case, we assume that either we have a unique fall in 0 or the limit of the function is positive as s goes to infinity. I want to show you one result that we establish for this model. For this case, f of 0 is equal to 0. In our study, we assume that f prime of 0 is equal to 1 in addition to f of 0 is equal to 0. For this model, we proved that this model has at least one positive solution for lambda bigger than a1 mu, at least three positive solutions for a certain range of lambda, and has at least one positive solution such that the subnorm of that solution goes to R naught as lambda goes to infinity. Here is an expected bifurcation diagram. Here is the case when R naught is infinite. That means there is no fall in 0. In that case, the subnorm of the solution will go to infinity as lambda goes to infinity. Here, this a1 mu is the principal eigenvalue of this eigenvalue problem, which is the linearized problem associated to our model. All right, now I want to introduce the model that I am interested in today. This is the elliptic system I'm interested in. As you can see in the equations, your unknowns are coupled, you here, and we here, and we over here. Okay, so unknowns are coupled in the equation, but on the boundary, they are not coupled. Okay, so I'm going to call this model number 1. Basically, we wanted to extend the results in the previous study to this model. In extending those results, we only focused on this case, f of 0 is equal to g of 0 is equal to 0, and we took mu lambda to be square root of lambda. That's what you have here. Okay, here are the hypotheses I'm going to have. We assume that f and g are increasing functions, and this particular limit is 0 for any positive constant m. And this kind of a condition is called a combined sublinearity. Okay, or in other words, f and g are combined sublinear. And this is my hypothesis 2. F and g are C1 functions on 0, a for some a positive, and f prime of 0 and g prime of 0 are positive. Next, I'm going to take E1 gamma to be the principal eigenvalue of this eigenvalue problem. The existence of E1 gamma follows from this paper by Goddard, Morris, Robinson, and Sivaji. Next, we can easily see that the principal eigenvalue of this problem, which is the associated linearized problem to our model, is going to be E1 gamma over g prime of 0, where gamma is 1 over square root of g prime of 0. I'm going to take this principal eigenvalue to be A1 from here onwards. Here are more terminologies. For b greater than a greater than 0, I'm going to define q1a to be the minimum of these two numbers and q2b to be the maximum of these two numbers. And I'm going to take c1 to be the infimum of this expression with respect to epsilon. Here, this n is the dimension of your domain, and r is the radius of the largest inscribed ball inside your domain. Okay. Finally, I'm going to take W to be the solution to this particular boundary value problem. Okay. Having said all that, I'm ready to state my results now. Here is the theorem 1 that we established. Let H1 and H2 hold. Then our model has a positive solution U lambda V lambda for lambda bigger than the principal eigenvalue, such that the subnorm of each individual component goes to infinity as lambda goes to infinity. Further, if there exists b greater than a greater than 0 such that this quotient is bigger than this number and q1 is bigger than this particular number, then our model has at least 3 positive solutions for lambda between this number and this number. Okay, and here q1 and q2 are defined as given here. Okay, here is an expected bifurcation diagram. You have at least one solution beyond A1 and at least 3 solutions for a certain range of lambda, and a solution u lambda such that the sup norm of u lambda goes to infinity as lambda goes to infinity. All right, here is theorem 2. If you take r bigger than 0 such that f and g are C2 functions on 0, r, and f prime of 0 is equal to g prime of 0 and they are both positive, and f double prime and g double prime are negative on the interval 0, r, then our model has a positive solution v lambda, u lambda, v lambda for lambda bigger than the principal eigenvalue but close to the eigenvalue, such that the sup norm of each individual component goes to 0 as lambda goes to A1 from the positive side. Here is an expected bifurcation curve. Okay, so we have a branch of the bifurcation diagram which is coming down to the trivial branch at A1. Okay, that's one bifurcation result that we proved. All right, to establish these results, we used method of sub and super solutions. Let me introduce method of sub and super solution. Any pair psi1, psi2 satisfying these 4 inequalities is called a sub-solution, and any pair C1, C2 satisfying these 4 inequalities is called a super solution of our model. Okay, here is an important lemma that we will be using in establishing our results. If we have a small sub-solution psi1, psi2 and a bigger super solution C1, C2 such that your super solution is bigger than or equal to your sub-solution, then the conclusion is that there has to be a solution u, v in between those 2 sub and super solutions. Here is the second lemma that I want to state. If we have a small sub-solution psi1, psi2 and a bigger super solution z1, z2 and another strict sub and super solutions in between those two, your strict sub-solution is such that the sup norm of the strict sub-solution is bigger than the sup norm of the strict super solution in at least at one point in the domain, then the conclusion is that you have a solution u1, v1 in this particular ordered interval, u2, v2 another solution in this particular ordered interval. Actually, the existence of these 2 solutions come as a consequence of the previous lemma, and there has to be a third solution in this particular space that can be proven using degree theory. All right, next I want to give you an outline of the proof of theorem 1. Theorem 1 is basically this bifurcation diagram. This is what I am after. Okay, we have a solution for lambda bigger than A1 and 3 solutions, at least 3 solutions for a certain range of lambda, and a solution u lambda such that the sup norm of the solution goes to infinity as lambda goes to infinity. All right, here is how the proof goes. Without loss of generality, I'm going to assume that f prime of 0 is greater than or equal to g prime of 0. First, I'm going to construct a small sub-solution psi1, psi2 for lambda bigger than the principal eigenvalue. Okay, to construct that sub-solution for a fixed lambda, I'm going to take sigma lambda to be the principal eigenvalue of this problem. Then here are some interesting results that you about sigma lambda. Sigma lambda has to be positive when lambda is less than A1. Sigma lambda is negative when lambda is bigger than A1, and sigma lambda is 0 when lambda is 0. Okay, this proof of these properties can be found in this paper by Goddard, Morris, Robinson, and Shivaji. Now I'm going to take psi1, psi2 to be this pair m phi lambda, m phi lambda. Phi lambda is the eigen function associated to this eigenvalue problem. To show that this is a sub-solution, I'm going to define this function h of s. Then we can immediately see that h of 0 is 0 because f of 0 is equal to 0, and h prime of 0 is going to be this expression. Now using the fact that g prime of 0 is less than or equal to f prime of 0 and sigma lambda is negative when your lambda is bigger than A1, we can see that this quantity is negative. You that this function has to be less than or equal to 0 if your s is small. That means this difference has to be less than 0 if you choose this term to be small. In fact, that term will be small if you choose your m small. So that means this has to be a sub-solution. This inequality holds if you choose your m small enough. Similarly, we can show that this difference is also less than or equal to 0. And if you look at the boundary expression, this one, this is clearly 0 because this phi lambda satisfies this boundary condition. Okay. Similarly, we have the other boundary term to be 0. That means psi 1 comma psi 2 is a sub-solution. So we have a sub-solution. Next, I'm going to construct this bigger super solution. To construct my bigger super solution, I'm going to take E lambda to be the solution to this boundary value problem. And I'm going to take C1 comma C2 to be this pair. Okay, I'm going to choose this M later. All right. Here, I'm going to assume that F and G are bounded. Even if they are not bounded, we can still get the proof going, but I don't really want to go into that today. Since F and G are bounded, we can choose this constant M big enough so that this quantity is bigger than this your right hand side. That implies that negative Laplacian C1 minus lambda f of C2 is bigger than or equal to 0. Okay, so we have the first inequality. Similarly, we can show this inequality. And if you go to the boundary, this boundary expression is going to be clearly 0 because E lambda satisfies this boundary condition. Okay. Similarly, we have the other boundary expression is equal to 0. So that means C1 comma C2 is a super solution, big super solution if you choose your M big. Okay. All right. Next, I want to construct an intermediate strict super solution C1 bar comma C2 bar for lambda between 1 and this number. Okay. To construct that, I'm going to take W to be the solution to this boundary value problem. And I'm going to take Z1 bar comma Z2 bar to be this particular pair. And now using the fact that lambda is less than this number, we have this inequality right here. Now rearranging the terms, we get this inequality over here. Now, using the fact that f is an increasing function, I can replace this a by a smaller quantity to get a smaller quantity in the right hand side. So we have this inequality. I'm replacing a by this quantity, which is smaller than a. Okay. So this implies that negative Laplacian Z1 bar minus lambda f of C2 bar has to be positive because this quantity is bigger than this one. If you move this to this side, it is just this difference. And similarly, we can show the other inequality. This difference is positive. And again, on the boundary, if you compute the boundary term, using the fact that your lambda is bigger than 1, we can easily see that this expression has to be bigger than 0. Similarly, this has to be bigger than 0. So that means C1 bar comma C2 bar is a strict super solution for our problem. Finally, we need a strict subsolution. To construct a strict subsolution, by the way, I'm constructing my strict subsolution for lambda bigger than C1 times Q2. Okay. To construct that, I'm going to look at this particular boundary value problem. This is the same, these are the same equations, but we have Dirichlet boundary conditions here. This problem was studied by Ali, Ramaswamy, and Shivaji, and they proved that this problem has a strict subsolution U0, V0, such that the subnorm of each individual component is bigger than B. And now I'm going to take psi1 bar comma psi2 bar to be the solution to this problem. The solution to this problem exists because your right-hand side is known. You are plugging your U0 and V0 and U0 for F and G respectively. So I'm going to take the solution of this problem to be psi1 bar comma psi2 bar. Then using the Hopf maximum principle, we can show that psi1 bar comma psi2 bar is bigger than the subsolution, strict subsolution of this problem. Okay. But since F and G are increasing, we have this inequality. This is of course negative Laplacian C1 bar is this expression, which is less than lambda times f of C2 bar because C2 bar is bigger than V0 and F is increasing. Okay. Similarly, we have this inequality right here. And of course, the boundary inequalities are clear because these two boundary terms are 0. Okay. So that tells you that psi1 bar comma psi2 bar is a strict subsolution. And notice that the subnorm of that subsolution is bigger than B, and the subnorm of the strict supersolution is A, which is less than B. So that means we have this situation. The subnorm of the strict subsolution is bigger than the subnorm of the strict supersolution. So we can apply our lemma 2 to conclude that our model has at least 3 positive solutions for lambda in this particular interval. Notice that this is the intersection of intervals that we used in constructing our subband super solution. For this range of lambda, we have at least 3 positive solutions. And to show that we have a solution u lambda such that the subnorm of that solution goes to infinity as lambda goes to infinity, I'm going to look at this particular boundary value problem. Here we take this h to be such that h of 0 is 0, h is less than or equal to both f and g, and the limit of h is positive as s goes to infinity. And if you consider this boundary value problem, these authors proved that this problem has a solution w lambda such that the subnorm of w lambda goes to infinity as lambda goes to infinity. Now I am going to take this ordered pair, this pair w lambda comma w lambda. We can easily see that this is going to be a strict sub-solution for our problem using Hopf maximum principle. Okay. And now by lemma 1 again, there has to be a solution between this w lambda comma w lambda and c1 comma c2. Of course, this we can make this c1 comma c2 as big as we want. Okay, so there has to be a solution between this sub solution and this super solution such that the subnorm of each individual component of that solution goes to infinity as lambda goes to infinity, because the subnorm of w lambda goes to infinity as lambda goes to infinity. Okay. So this establishes this complete bifurcation diagram. Finally, I want to show you some references that I was using in my talk. And here are some references where you can find these types of models where you can see this parameter influence on the boundary. Thank you for your attention.